Hello again and welcome to our course on software quality. We have discussed quality and its basic components, product requirements and processes, and our topic for some next weeks is verification, testing and validation. We start with testing, and today's topic is the verification, testing, validation concepts and 5 first and fast methods for software testing. So key points to know. We start with testing and test. So let's see what is testing. Many notions of testing exist. Some are broad, some are narrow. The notion we use in this course is dynamic verification of the behavior of a program on a set of test cases. The executions domain is usually very large or infinite against the expected behavior. So this says that testing is dynamic activity, not just sitting on a desktop desk and viewing some code, but typically executing the program and comparing the results against expected results. There are also more wide definitions for testing. For example, testing as the process which includes all lifecycle activities, both static and dynamic, includes planning, preparation, evaluation, software products, and related work products. We will not use this one because we want to distinguish between static and dynamic properties and verification. But otherwise, it's of course also an applicable definition. So testing. Now, what is test? If we agree that testing means dynamic investigation of behavior against expected behavior, then we must also accept that test includes both inputs and expected outputs. Sometimes test is defined to include a set of test cases, and each test case includes inputs and expected outputs. But the important thing is that we need to have the outputs. If we just say that let's test with values 3, 4 and 5, this doesn't say anything about the outputs. So we need to have inputs and outputs. More broadly, a test also includes preconditions. For example, if you test a ATM, then money has to be loaded there, and so on. Preconditions and postconditions. For example, if you test whether a client can register in a client database, then the postcondition is that the client has registered. Her data are in the database. Some more concepts. Verification. Verification is checking conformance to the previous stage of development. We may verify implementation against design or design against specification. Validation checks the final result against initial needs. So we have software which has been delivered, which is operating. Does it satisfy the needs? It's often said that verification checks whether we are doing the things in the right way, while validation checks whether we have done the right things. Certification means activity of a third party who evaluates some products or organizations against given legislation, requirements, and so on. Debugging means finding the causes of failures. So if software is behaving in a way which is not expected, then why this is so, how to improve it. These are questions of debugging. Error, fault, and failure, they are used in different settings. They are used in a different way. But one way to use them is that somebody makes an error. This is human behavior, which is not correct. As a result of this error, we have a fault in the program. And as a result of this fault, when I execute the program in its intended environment, there may be a failure and some expected results or behaviors are not delivered. Our next question is, what is the goal of testing? And what is successful test? These are interdependent. So the short answer is that it depends. In different environments, different settings, the goals of testing may also differ. For example, in the first phases of software development, the goal of testing would be to find errors. So a successful test is a test which finds error, and a good test is a test which has a high probability of finding errors. This may seem somewhat controversial, because we might expect that testing is successful when the system passes and can be delivered to customers. And indeed, in the final phases of development, for example, in acceptance testing, the goal of testing might be to ensure or demonstrate that the software indeed conforms to requirements. So there the goal of testing is different. In certification, again, the goal of testing may be different, and so on. So goals of testing depend on a stage where testing is performed, and it can be very different. If you look at main software development life cycles, then in some of these, testing has an obvious place. For example, in waterfall, testing is one of the phases in the waterfall life cycle, or during a test-driven development, testing is obviously one of the main components throughout the whole life cycle. It may be not so obvious in some other development life cycles, but still in many types of life cycles, testing remains an important activity. For example, in V-model, it's included in pair to every lifecycle stage. In XP, we have several kinds of testing and so on. If we look at software development lifecycle models, we can see that most often we can locate where and which kind of testing exists in these life cycles. So we have looked through some notions pertaining to verification, testing, and validation, and we might ask what these activities here mean or what they are. For example, executing software with a series of inputs and comparing outcomes obviously is testing. Documentation review, from this our narrow testing point of view, is not straightforwardly testing. It's more a static activity. If we try to find out why the ambulance dispatch system cannot find the nearest ambulances, then we may be dealing with debugging and so on. Here are some more questions. We discussed these on the lectures. After this overview of main concepts in verification, testing, validation, let's proceed to some first methods for testing. We already saw that in different lifecycle models there are different stages, different stakeholders for testing. Now let's have a look at some fast to learn and cost-effective testing methods. So this is the primary property, why they are included together. They are mostly not very systematic and not very deep, do not require deep technical knowledge on testing or software development, but they still are main or additional components in several development frameworks. They are very useful. If we say that they are cost effective, this means that they might be used in the first place, so before or in addition to more systematic methods. And of course, when there is no sufficient time or resources for testing. First, ad hoc testing. It is something people do when they don't know what testing means. So we might say, oh, I need to test this software, let's give these inputs and see what happens. This is not testing from our formal point of view, but still it is definitely a very useful activity and absolutely better than nothing. Then smoke testing. Smoke testing is the first test and trying to understand whether something works at all. It comes from electronics. If we have some hardware and plug it into electricity network, then if smoke comes out, then it doesn't work. So that's the idea. Usual smoke testing is hello world. So if we have some programming environment or whatever system which we want to start using, then very often the main effort is devoted to its installation and getting it to function in our environment. And if we get this very, very simple test, hello world, it just outputs something, then we have done, well, sometimes half of our work. The remaining part may be much easier. So smoke testing is, of course, also a useful approach to testing. It's clearly not, these methods are clearly not sufficient for more critical systems, and they should be applied. Usually smoke testing is always applied. Some ad hoc testing may be performed by users, for example. Perhaps we couldn't say straightly they should not be used, but it would be more correct to say that they are just not sufficient in many cases. Well, let's proceed to some advanced test design technique, which still doesn't require too much knowledge about testing as such. So experience-based testing, where test cases are derived based on the tester's experience. And this experience, well, knowledge and intuition, may include many different facets or areas. We may have some general knowledge about how a software should function. For example, what are typical screens, what is typical behavior of software. We may know something about the application domain, what happens in this application. We may know something about typical defects in this area or in this programming tool. We may know something about some specific developer or customer or development process, and so on. Here is an example, fine for delay, where we have as inputs deadline, payment, amount, and fine percent per day, and we want to find fine. Now we can have different expert knowledge here. For example, we might know something about how the fines are calculated according to our legislation, which would be application domain area knowledge. We could know something about typical errors associated with dates and deadlines, which might be some programming and functions, knowledge about programming and functions. We might know something about security and errors made in processing, which again is a very specific knowledge about what kind of errors are done in an application development, and so on. So different kinds of expert knowledge may be used to find errors by this method. The fourth method in this group is exploratory testing. It is also an informal test design technique where the tester actively goes through the tests, designs the tests, during testing, learns during testing, and based on this learning, designs new tests and tries to find errors as fast and efficiently as possible. Exploratory testing is often performed if we do some hacking or security testing. Then what is being done is very often just this exploratory kind. We find new information about this particular application, and we try to use this information to go forward and discover new breaches. A final method in this group is risk-based testing. In its simplest form, it includes risk identification, assigning priorities, testing the most critical risks, and then informing the stakeholders against these risks. There exist many methods for risk analysis, but we will go through risk-based testing only on a very initial way, in its simplest form. Let's first ask where the risks can be identified. There are many places starting from the functionality. So our first question might be, what is the most valuable functionality? And obviously, if we need this software, if it's critical for our business or our activities, then here is one risk, that this most valuable functionality will not be delivered. Then the next point where to find or search risks are non-functional requirements. The reason is that functionality is straightforward. We can see directly whether the needed functions exist or not. Non-functional requirements may often be more difficult to test and not so easily seen. We must, for example, for load testing, we must make some heavy preparations sometimes, and so on. So this is the place to look for risks. Safety is the next question. Sometimes safety is related to functionality, sometimes it's not. For example, safety may refer to whether some critical industry system will explode or cease to function, which would result in great losses to environment, business, or even lives. It's not always related to functionality, at least not directly. So that's why we include it separately from functionality. Risks are associated with technical issues such as software complexity. We have seen very large projects to fail because they are just too complex to handle simultaneously. Somehow they should be divided, and if this division is not done, or if it's not correct, successful, then there is a risk. Novelty of an application or environment and so on, large data volumes are a source of risk, and so on. Development items, strict deadlines, scarce resources, a new team who has not worked together. Many such things provide places where to search and find risks. It's not always possible to test the risks. For example, if we have a new team, then we don't know whether this is a risk until we have done some work, or at least not always. We don't always have time to test these risks. If we characterize risks, then a typical matrix for risks is a likelihood. So that's how likely the risk is and its impact. Whether it's low, average, high impact, likelihood may also be low, average, high, or this is 3 degrees of likelihood and impact. We might also have 5 or so. But depending on these characteristics for low likelihood and low impact risks, we might say that the risk is low. For low impact and likely events, we might say that it's medium. For high impact, low likelihood risks, we might say that it's a higher risk. And for high likelihood, high impact risk, we might say that it's critical. And if you look at this matrix, you see that it's asymmetric. These things here are different. So in a way, impact may be more important than likelihood, but it depends, of course. So we have briefly gone through 5 methods, 5 fast and first methods of software verification, testing, validation, testing mostly. And it may be helpful to think about the following summary about each method we have gone through so far, or we go through in the future. We discuss it concept. We have, for example, we have seen what's the concept of risk-based testing. We explore risks and we develop tests against each risk. Preconditions. So what must exist in order to do, let's take the same example, risk-based testing. Obviously, we need to have some resources and time to do risk assessment and analysis. This is not always so this is a precondition. Advantages. An obvious advantage is that from the business point of view, risk-based testing addresses the most critical issues that may arise. For example, in expert-based testing, we might find some errors which never show up in actual operation. But in risk-based testing, we always find the most important ones from the customer point of view. Now, nothing is absolutely good or ideal, so we have also disadvantages, and here are just examples of disadvantages for risk-based testing. So risk analysis may be costly. It may not find out some risks associated, for example, with development, with application area, and so on. So what are the results of risk-based testing? We have tested our software against the main business risks, which is a very desirable result. And that's why risk-based testing is, for example, recommended for acceptance testing. Relationship to other methods. It's complementary. You can use it together with the other methods. Evaluation. It depends on the environment, on the case, of course. If there are no large business risks or the software is not critical, why trouble ourselves with risk-based testing? But otherwise it's a very useful thing. And there are some tools related to, for example, to risk assessment. We may use tools to store the tests and perform testing and so on. So this was a short walkthrough of these properties for risk-based testing. Please do the same exercise for the other kinds of methods of testing we have concerned here, and for the other methods that will come in this course. Now, a very practical question is in which order we should do our testing. And an obvious answer is that, well, let's take the cheap ones first. Or another obvious answer would be that let's take these methods first, which are naturally included in the software development lifecycle. So this is not some kind of absolute order, but here are some hints. First, to provide software, we have to develop it, right? And if we do development, then we do some testing anyway. So developer testing is one of the very first things to do. Smoke test is the first thing to try software. And of course, ad hoc testing could be very, very cheap. We have already discussed that all these methods are not sufficient, but they're useful. Risk-based testing is not so cheap anymore, but it will find critical issues for their customer. So that's why it's very important. Exploratory testing and experience-based testing are not included as very cheap, but they may be very cost-effective. They are not cheap because they require some specific knowledge and expertise. And this may be not cheap. For example, if you hire an expert, it may cost quite a lot. But it is possible to have good results and find errors which cannot be found with any other method sometimes. So very efficient. There are some fundamental questions related to testing, and one of these is how much should we test? Ideally, one might say that we test until the software is reliable or until there are no errors or faults in software. For many reasons, this approach is not viable, possible even. And one of the reasons is that in any practical system there are so many possible inputs, meaning not just inputs from the user, but from the environment, from other software, other systems, and so on, that it's not possible to test software until it's correct. Just not possible. So we could make this ideal easier or more flexible and say that our requirements should define our testing volume. For example, if the requirement is a reliability or availability measure, then we should test until this reliability or availability has been achieved. Practically, it's not always possible. It's not always possible to evaluate whether the requirements have been satisfied. The requirements sometimes do not exist to this level that we can test against them. Some more dirty reasons: work must be done fast, or there is no resources, is another name for this reason. Some practical possibility to determine testing volume: if the team is experienced, then the team's experience may determine testing volume. Of course, this application is not critical, then extensive testing is not needed, or sometimes testing only some very rudimentary or initial testing is needed. So the question of how much to test we leave for the future, but let's say that that it's not so easy to answer. It depends on the overall quality topics, on the product requirements and processes, and some advanced possibilities to determine testing capacity. So these pragmatic things are that requirements as a whole determine testing volume, or our experience, or our resources. But there are some criteria that evolve from our testing methods that we shall look into in the future weeks. So all essential data combinations, equivalence classes, the satisfaction of some criteria depending on the source code, or criteria on reliability, and so on. As a summary, why can't we just do some ad hoc testing and be satisfied? Well, if the application is not critical, this may be the case, but for more sensitive, more critical applications, the testing methods that we are going to further analyze in this course, they improve testing efficiency. We achieve good results more easily than without them. They enable test design and repetition. They enable systematic testing, and they enable outside evaluation. So if we say that we just tried this system with some inputs, nobody can say what this means, whether the system has been tested or not. But if we say that, for example, we satisfied some code-based criteria, then this already says that we have investigated, analyzed our software to some degree of precision. Additional reading is available in a lots of sources, and as always, these materials are available on Moodle and on Tapandi.ee. So thanks for listening. We will discuss these topics more deeply in the lectures and in exercises, and see you again.